Hello, everyone. Welcome back. This is part 5 in our series on distributed word representations. We're going to be talking about dimensionality reduction techniques. We saw in the previous screencast that reweighting is a powerful tool for finding latent semantic information in count matrices. We're going to push that even further. The promise of dimensionality reduction techniques is that they can capture higher order notions of co-occurrence corresponding to even deeper sorts of semantic relatedness. There's a wide world of these dimensionality reduction techniques. I've chosen 3 that we're going to focus on as interesting representatives of a much larger space. We'll look at latent semantic analysis, which is a classic linear method. Then we'll talk about autoencoders, a newer, powerful deep learning mode for learning reduced dimensional representations. And then finally, GLOVE, which is a simple yet very powerful method that, as you'll see, has a deep connection to pointwise mutual information. And then I'm going to close by talking briefly about visualization, which is another kind of dimensionality reduction technique that we might use for very different purposes. So let's begin with latent semantic analysis, a classic method. The paper is due to Deerwester et al. 1990. That's a classic paper that really made a splash. It's one of the LSA is now one of the oldest, most widely used dimensionality reduction techniques, not only in scientific research, but also in industry. I think it was really eye-opening for people at the time of the paper's appearance to see just how powerful this technique could be, especially in contexts involving information retrieval. The method is also known as truncated singular value decomposition, and I'll explain why that is in a second. The final thing I want to say at this high level is just that LSA remains a very powerful baseline, especially when part of a pipeline of other reweighting methods. So it should probably be in your results table, and it's often very difficult to beat. Now, I think we can't, in the time allotted to us, cover all of the technical details surrounding latent semantic analysis. In my experience, this would be kind of the culmination of a full course in linear algebra. But I do think I can convey the guiding intuitions, and that will help you with responsible use of the method. So let's imagine that we have this simple 2-dimensional vector space model. I've got 4 points, A, B, C, and D, arrayed out in this 2-dimensional space. I think we're all familiar with fitting linear models, which capture the largest source of variation in the data. That's this orange line here. And the perspective I would encourage you to take is that we can think of that linear regression model as performing dimensionality reduction in that it encourages us to project points like B and C down onto that line. And in projecting them down onto that line, essentially in abstracting away from their point of variation along the y-axis, we can see the sense in which they are abstractly similar. They're close together in this reduced dimensional space. Now, with the linear model, we captured the source of greatest variation in this little data set. In a high dimensional space, we could continue fitting lines to other sources of variation in the data, other axes of variation. So here's a blue line here that captures the next dimension. And we could again project points like A and C down onto that line, and that would capture the abstract sense in which A and C, although very spread out along the x dimension, are very close together along the y dimension. And of course, if we had more dimensions in this vector space model, we could continue to perform these cuts and dimensionality reductions, capturing ever more abstract notions of similarity along these different axes. And that is, in essence, what LSA is going to do for us in our really large matrices. The fundamental method, as I said, is singular value decomposition. This is a theorem from linear algebra that says any matrix of dimension m by n can be decomposed into the product of 3 matrices, T, S, and D, with the dimensions given. Here's a more concrete example. Start with this matrix of dimension 3 by 4. We learn a term matrix, which is full of length normalized orthogonal vectors. We have this matrix of singular values along the diagonal. They are organized from largest to smallest, corresponding to the greatest to least source of variation in the data. And then we have the document or column-wise matrix, which is also length normalized and orthogonal in its space. And the theorem here is that we can reconstruct A from these 3 matrices. Of course, we don't want to precisely reconstruct A. That probably wouldn't accomplish very much for us. But what we can do is use this to learn reduced dimensional representations of A by being selective about which term and singular value dimensions we include in the model. Let me walk you through an example of how that happens. And first, let me motivate this a little bit with an idealized linguistic case. So I've got up here a word by document matrix. Its vocabulary is gnarly, wicked, awesome, lame, and terrible. And the conceit of my example is that both gnarly and wicked are positive terms, so they tend to co-occur with awesome and not co-occur with lame and terrible. However, gnarly and wicked never occur in the same document. The idea is that gnarly is a slang positive term associated with the west coast of the United States, and wicked is a slang term associated with the east coast of the United States. In virtue of that idealized dialect split, they never occur in the same document. But nonetheless, they have similar neighbors in this vector space, and that's the kind of abstract notion of co-occurrence that we want to capture. If we simply use our standard distance measures and reweighting techniques and so forth, we will not capture that more abstract notion of co-occurrence. Here are distances in this raw vector space: gnarly, awesome, terrible, and wicked. Wicked is farther away from gnarly even than terrible is. So we've got a sentiment confusion and really just not the result we were shooting for. So we perform singular value decomposition into these three matrices. And then the truncated part is that we're going to consider just the first two dimensions of the term matrix corresponding to these two singular values, capturing the top two sources of variation in the data. So we multiply those together and we get this reduced dimensional matrix down here, 2 by the size of the vocabulary. And if we do distance measures in that space, just as we were hoping, gnarly and wicked are now neighbors. The method has captured that more abstract notion of having the same neighbors as the other word. In the previous lecture, I encouraged you to think about what you're doing to a matrix when you perform some kind of reweighting scheme. Let's extend that to these dimensionality reduction techniques. So here's a picture of what LSA does, starting with a raw count distribution over here. If I just run LSA on that raw count distribution, I get what looks also like a very difficult distribution of values. The cell values are very spread out, and they have a lot of the mass centered around 0 here, corresponding to the peak in the raw counts over here near 0 as well. So that doesn't look like we've done very much in terms of taming the kind of untractable skewed distribution we started with. However, if instead we take the raw counts and first feed them through PMI, which as we saw before, gives us this nice distribution of values, highly constrained along the x-axis, and then we run LSA, we retain a lot of those good properties. The values are somewhat more spread out, but still nicely distributed. This looks like a much happier input to downstream analytic methods than the top version here. And I think this is beginning to show that it can be powerful to pipeline reweighting and dimensionality reduction techniques. Another note I would want to make: how do you choose the dimensionality for LSA? It has this variable k corresponding to the number of dimensions that you keep. If you read the literature on LSA, they often imagine this kind of what I've called the dream scenario, where you plot the singular values and you see that a lot of them are very large and then there's a sudden drop off. And if you do see this, then it's obvious that you should pick the point of the sudden drop off as your k. So here you would pick k as 20, and you'd be confident that you had captured almost all the variation in your data in the reduced dimensional space you were creating. Unfortunately, for the kinds of matrices and problems that we're looking at, I really never see the dream scenario. What I see looks something much more like this, where you have kind of a sudden drop off early and then a long decline and maybe a sudden drop off at the end. And it's basically totally unclear where in the space you should pick k. And the result is that k is often chosen kind of empirically as a hyperparameter tuned against whatever problem you're actually trying to solve. If in doing this work you do see the dream scenario, please do write to me. It would be very exciting to see that happen. LSA is just one of a large family of matrix decomposition methods. Here's a list of a few of them, and a lot of them are implemented in scikit-learn in its decomposition library. And I would encourage you to try them out and just see how they perform on problems that you're trying to solve. And finally, here's a little bit of code. vsm.lsa, so with k set to 100, gives me back a reduced dimensional version of that matrix, keeping the same vocabulary, of course, but now with only 100 column dimensions. Let's move to autoencoders. This will be a point of contrast with LSA because this is a much more powerful method. So here's the overview. Autoencoders are a flexible class of deep learning architectures for learning reduced dimensional representations. If you want to hear much more about this class of models, I would encourage you to read chapter 14 of the Goodfellow et al. Book, Deep Learning. It has a lot of details and a lot of variations on this theme. Here is the basic autoencoder model. The input would be say the vectors from the rows in our matrices. So this could be the counts or something that you've done to the counts. Those are fed through a hidden layer of representation. And then the goal of this model is to try to literally reconstruct the input. Now, that might be trivial if H had the same dimensionality as X, but the whole idea here is that you're going to feed the input through a very narrow pipe and then try to reconstruct the input. Given that you're feeding it through a potentially very, very narrow pipe, it's unlikely that you'll be able to fully reconstruct the inputs. But the idea is that the model will learn to reconstruct the important sources of variation in performing this autoencoding step. And then when we use these models for representation learning in the mode that we've been in for this unit, the representation that we choose is this hidden unit here. We typically don't care about what was reconstructed on the output, but rather only about the hidden reduced dimensional representation that the model learned. This slide has a bunch of other annotations on it, and the reason I included them is that the course repository includes a reference implementation of an autoencoder and all the other deep learning models that we cover in pure NumPy. And so if you wanted to understand all of the technical details of how the model is constructed and optimized, you could use this as a kind of cheat sheet to understand how the code works. I think the fundamental idea that you want to have is simply that the model is trying to reconstruct its inputs. The error signal that we get is the difference between the reconstructed and actual input. And that error signal is what we use to update the parameters of the model. Final thing I would mention here is that it could be very difficult for this model if you feed in the raw count vectors down here. They have very high dimensionality and their distribution is highly skewed, as we've seen. So it can be very productive to do a little bit of reweighting and maybe even dimensionality reduction with LSA before you start feeding inputs into this model. Of course, it could still be meaningful, even if you've done LSA as a pre-processing step, to learn a hidden dimensional representation, because this model is presumably capable of learning even more abstract notions than LSA is in virtue of its nonlinearity at this hidden layer. And here's a bit of code just showing how this works using both the reference implementation that I mentioned, as well as a faster and more flexible Torch autoencoder, which is also included in the course repository. I think the only interface thing to mention here is that these models have a fit method, like all the other machine learning models for this, but the fit method returns that hidden dimensional representation, the target for our learning in this context, which is a bit non-standard, but it's the intended application for this kind of representation learning. The other thing I would mention is, so let's see how well the autoencoder is performing. This is the raw distances in the Giga5 matrix for finance. This is the count matrix. It doesn't look great. If we run the autoencoder directly on the count matrix, it looks a little better, but it's still not excellent. If we think of this as part of a pipeline where we've first done positive pointwise mutual information, and then LSA at dimension 100, and then done the autoencoding step, it starts to look like a really good and interesting semantic space. And I think that's pointing out the power of including the autoencoder in a larger pipeline of pre-processing on the count matrices. Okay, let's turn to GLOVE, or global vectors, for the final major unit for this screencast. Here's a brief overview. GLOVE was introduced by Jeffrey Pennington, Richard Socher, and Chris Manning, a Stanford team, in 2014. Roughly speaking, the guiding idea here is that we want to learn vectors for words such that the dot product of those vectors is proportional to the log probability of co-occurrence for those words. And I'll elaborate on that in a second. For doing computational work, we can rely on the implementation torchglove.py, which is in the course repo. I'll mention that there's also a reference implementation in vsm.py. It's very slow, but it kind of transparently implements the core GLOVE algorithm, so it could be interesting to inspect. And then if you're doing practical work with really large corpora and really large vocabularies, I would encourage you to use the GLOVE Team C implementation. It's an outstanding software artifact that will allow you to learn lots of good representations quickly. And that kind of brings me to my last point. I just want to mention that the GLOVE team was among the first teams in NLP to release not just data and code, but pre-trained model parameters. Everyone does that these days, but it was rare at the time. And I think this team is kind of really forward-thinking and seeing the value of releasing these centralized resources. And a lot of really interesting work happened with GLOVE vectors as a foundation. All right, so let's think about the technical aspects of this model. This is the GLOVE objective, and you're going to see pointwise mutual information kind of creep into this picture in an interesting way. So this is equation 6 from the paper. It's kind of an idealized objective for the GLOVE model. And it says what I said before. We have a row vector and a column vector, wi and wk. We're going to get their dot product. And the goal is to learn to have that dot product be proportional to the log of the probability of co-occurrence of word I and word K, where the probability of co-occurrence is defined in the way that we defined it before when we were talking about row normalization. It's just done in log space. This is the co-occurrence count. This is the sum of all the counts along that row. And basically in log space, we're just dividing this value by this value. So keep that in mind. Now, the reason they have only the row represented is that in the paper, they're assuming that the rows and columns in the underlying count matrix are identical. And so we don't need to include both. However, if we did allow that the row and context could be different, we would just elaborate equation 6 to have a slightly different denominator, right? We would have the product of the row sum and the column sum and take the log of that and subtract that out. And that would be kind of our goal for learning these dot products here. But this is where PMI sneaks in, because that simply is the PMI objective, right? Where we stated that as the log of the probability of co-occurrence divided by the product of the row and the column probabilities. Here they've just stated exactly that calculation in log space, and these are numerically equivalent by the equivalence of log of x over y being the same as log of x minus the log of y. So that's the deep connection that I was highlighting between GloVe and PMI. And I think that's really interesting because it shows that fundamentally we're testing a very similar hypothesis using very similar notions of row and column context. Now, the GloVe team doesn't just stop there. The GloVe objective is actually much more interesting as an elaboration of that core PMI idea, but it's worth having PMI in mind because it's there throughout this presentation. In the paper, they state this is a kind of idealized objective where we're going to have the dot product, as I said before, in two bias terms, and the goal will be to make that equivalent to the log of the co-occurrence count. That has some undesirable properties from the point of view of machine learning, so they propose in the end a weighted version of that objective. You can see we still have the dot product of the row and the column vectors and two bias terms. We're going to subtract out the log of the co-occurrence count and take the square of that. And that's going to be weighted by f of the co-occurrence count, where f is a function that you can define by hand. And what they do in the paper is set it with two parameters, x max and alpha. For any count that is above x max, we're going to set it to 1 to kind of flatten out all the really large counts. Everything that's below x max, we will take as a proportion of x max with some exponential scaling as specified by alpha. That's the function there. And typically alpha is set to 0.75 and x max to 100, but I encourage you to be critical in thinking about both those choices and how they relate to your data. I'll return to that in a second. So GloVe really has these three hyperparameters: the dimensionality of the learned representations, x max, which is going to have this flattening effect, and alpha, which is going to scale the values, right? And so here's an example of how those are interacting, x max and alpha. If I start with this vector 100, 99, 75, 10, and 1, the function f, as we specified it, is going to flatten that out into 1, 99, 81, 18, and 0.03. You should just be aware that that kind of flattening is happening. So GloVe learning, so it's kind of interesting to think about analytically about how GloVe manages to learn interesting representations. And one thing that might be on your mind is the question, can it actually learn higher order notions of co-occurrence? That's been the major selling point of this lecture. I gave that example involving gnarly and wicked with LSA. Is GloVe going to be able to do that, right? We could just pose that as a question. So let's start that and see what happens, see how this works. The loss calculations for GloVe, this is kind of a simplified version of the derivative of the model. And we're going to show how GloVe manages to pull gnarly and wicked toward awesome in that little idealized space that I used before. I'm going to leave out the bias terms for simplicity, but we could bring those in. And so here's how this is going to proceed. What I've done just for this idealized example is begin in a GloVe space where wicked and gnarly are as far apart as I could make them. So as different as I could possibly make them. I've got awesome and terrible, and awesome is kind of close to gnarly already. What you'll see is that after just one iteration of the model, what has happened is that wicked and gnarly have been pulled toward awesome. And that's just the kind of effect that we wanted. That's the sense in which GloVe can capture these higher order notions of co-occurrence. And just in a little more detail, you might want to study this on your own, but the high level overview of exactly how that learning happens proceeds as follows. We start from these counts up here. And the crucial assumption I'm making is that wicked and gnarly never co-occur, but they occur a lot with awesome. And awesome will be kind of the gravitational pull that makes gnarly and wicked look similar. Keep in mind that because of that function f, by and large with GloVe, we're dealing not with the raw counts, but rather with the reweighted matrix. And that preserves this property that they never co-occur, and it gives differently scaled values for the rest of the co-occurrence or pseudo co-occurrence probabilities. All right, and then here's what we're going to track. This is the gnarly vector in 0, and you can see I've made them as far apart as I could. They're kind of opposed to each other. And we're going to see how they get pulled toward awesome in the context vector. So this is that loss calculation. I have just plugged in all the values here, and you can see that we get this initial set of losses. That's after one iteration. We update the weight matrices, and we perform one more round of learning, and you can see that both of these models, the values here are getting larger, corresponding to getting pulled closer and closer toward awesome. And you can see that graphically happening over here in these plots on the left. And as I do more iterations of the GloVe model, this effect is just going to strengthen, corresponding to wicked and gnarly, getting pulled toward awesome and away from terrible as a result of these underlying counts. And I take this as good evidence that GloVe, like the other methods we've discussed, is capable of capturing those higher order notions of co-occurrence that we're so interested in pursuing with these methods. Let's close the loop also. We have those central questions. What is GloVe doing to our underlying spaces? With GloVe, because of the design of the matrix, we have to begin from word by word co-occurrence matrices of counts. So we begin with these raw count values, and GloVe is one-stop shopping. It's going to take us all the way to these reduced dimensional representations. And boy, by the criteria we've set up, does GloVe do an outstanding job. This is the result of running GloVe at dimension 50. And you can see that the values are extremely well scaled between -2 and 2 and nicely normally distributed. This is an outstanding input to modern machine learning models. And I think this is probably a non-trivial aspect of why GloVe has been so successful as a kind of pre-trained basis for a lot of subsequent machine learning architectures. And then here's a little bit of code, just showing you how you can work with these interfaces using our code base. The one thing I wanted to call out is that I'm trying to be careful. I have defined this function percentage non-zero values above, and you can set Xmax here and just feed in a matrix and study what percentage of the values in that matrix are going to get flattened out to 1 as a result of the Xmax that you've chosen. And this value really varies by the design of the matrix. If I feed in Yelp 5, only about 5% of the values are getting flattened out. But if I feed in Yelp 20, which is much denser and has much higher counts, 20% of the values are getting flattened out to 1. You know, if this number gets too high, the matrix might become completely homogeneous. And so we should really be aware of how the setting of Xmax is affecting the kind of learning that we could even be performing with GloVe. And it might turn out that this is even more important than the number of iterations or the dimensionality of the representations that you learn. Once you've made those choices, though, the interface is pretty clear, and the fit method, as with the autoencoder, returns the matrix of learned representations that we want to use for the current purposes. And then finally, I've included a score method. And the score method is literally just testing to see how well the vectors that you've learned correspond to the GloVe objective of having the dot products be proportional to the log of the co-occurrence probabilities. And you can get a score for that. We're doing pretty well here, I'd say, for a large empirical matrix. Final section, let's just say a bit about visualization. And this is a dimensionality reduction technique in the sense that the whole point is to try to flatten out a very high dimensional space into possibly 2 or 3 dimensions. You have to recognize that inevitably this will involve a lot of compromises. It's just impossible to capture all the sources of variation in your underlying matrix in just a few dimensions, but nonetheless, this can be productive. I think it's especially valuable if you pair it with some kind of hands-on qualitative exploration using something like VSM neighbors to understand at a low level what your matrix encodes. And then the high-level visualizations can be a kind of counterpart to that. There are many visualization techniques, and a lot of them are implemented in the scikit manifold package. So I encourage you to use them. I'm going to show you some results from TSNE, which stands for T-distributed stochastic neighbor embedding. There are lots of user guides there that you can study for more details. Let me just give you the high level. This is TSNE run on our Giga 20 matrix. I think this is typical of pretty good output from TSNE. So what we're seeing here is some pockets of high density. Those are areas of local coherence. Globally, we should be careful not to overinterpret this entire diagram because As you rerun the model with different random seeds, you'll see that it gets kind of reoriented in different parts or correspondingly close to different other parts. But what you can count on pretty reliably is that these local pockets of coherence correspond to coherence parts of the space that you've defined. And if you zoom in on them, you can kind of assess what the model has uncovered. So for this Giga21, for example, I think we see prominent clusters corresponding to things like cooking and conflict. If we do the same thing for our Yelp matrix, again, this looks pretty good in terms of having some substructure that we could analyze. And if we zoom in, we do see clusters like positive terms and negative terms corresponding to the evaluative setting of these Yelp reviews. So this is all very encouraging and suggests that the underlying spaces have some really interesting structure that might be useful for subsequent analysis. And here are some code snippets. We have this simple wrapper around the scikit to SNE implementation that will allow you to flexibly work with this stuff using the count matrices from our unit. And I'm just mentioning here that it's pretty easy if you wanted to color code the words in your vocabulary, say according to a sentiment lexicon or some other kind of lexicon. That could be a way for you to reveal exactly what structure your model has been able to uncover with respect to those underlying labels, and that can be useful.